Okay, so that Learn Smart assignment was assigned last week, is due at the end of the day today. So make sure to get on there. It should take about 10 minutes. Kind of introduces the topic that we're going to talk about today. I'll show you some kind of useful things in Excel, hopefully, if we have time today as well. After Thanksgiving break, I'll just kind of record, I'll have a Zoom, I'll get some Zoom links up there on Canvas so you can log on and you can ask me questions while I'm kind of recording the lectures, but basically this is kind of the last topic that we'll cover. Other than that, I'll probably do some review sessions kind of prior to that final exam week, okay? So, where are we here? So I started to kind of introduce this idea last week of linear regression, okay? So the idea is, if we were able to observe our data, let's say we have two variables, X and Y, it could be income and education. If we just plot kind of each one of those observations, we'd have like a scatter plot. This is going back to like week 2. What we're going to try to do is, well, look, if we try to draw a line of best fit, a line that best fits this data, it would have some intercept A and it would have some slope, which I'm going to call B. Right? And that slope represents the relationship between X and Y, right? We think about this as just any general example. So let's say I've got this line of best fit. Here's the intercept. If I go over 1 unit, right, X goes up by 1, how much the Y value goes up is essentially, if I'm looking at that first unit, right, 0 to 1, it's whatever that slope of that line is, right? If my X goes up by 1, my predicted Y value, my Y value here goes up by whatever that value B is. So we're interested in what that relationship is, what that value B is, because it tells us what that relationship between X and Y is, right? So if we think about different examples, I think we did these last class, but just kind of a reminder. When I think about some data that looks like this, my slope here would just be 0 as X goes up, Y doesn't change by anything. Here, thinking about my slope, my value B is going to be positive as X goes up, Y is also going up, right? And then here, as X goes up, Y is going down, which would be my slope there is going to be negative, right? So kind of the 3 different kind of ranges that we're thinking about. I said we can also do some of these nonlinear relationships. We're not going to do anything with that in this class, but kind of moving forward, if you were to continue on with statistics, you would start to be able to analyze kind of different ways to estimate these nonlinear relationships, right? But we won't kind of focus on those. So how do we get this line of best fit, right? We have this equation, right? And another thing that I think I had mentioned last class with this equation, right, is going to allow us to come up with predicted Y values. So in the data, we can observe the actual Y values. We're going to come up with these estimates for what the intercept or what the constant is, but also an estimate for what the slope is, right? Then if you tell me any X value, I plug that X value in, and I can tell you what that predicted Y value is. Once I have numbers in here, or once I have estimates for, that slope and that intercept. Okay? So how do I get those estimates, right? I've got all this data. I could draw, if I had a bunch of observations, I could draw my line of best fit, and then I could figure out what the slope is. But I mean, in practice, we can't just draw a line to the data, but we do want to know where is that line located. So the way we can figure out where that line of best fit is located is essentially, we can think about every single Y value. If we were to use, even once we have those estimates for A and B, we could come up with a predicted Y value. The problem is, for any given observation, we're going to have what we call this error term or this epsilon, right? So if you think about, if I had a bunch of data, I could try to estimate the years of education someone has on their income, right? So my Y variable there is income, my X variable, thinking about is years of education. The problem is if I look at someone like Bill Gates and I try to just plug in their years of education, I can come up with a predicted income, which might be like the average income of, kind of think about it as the average income of someone with a, 16 years of education or high school or college graduate, even though the problem is I can come up with that predicted value, but for Bill Gates, he's going to be making way more, right? My prediction is going to be off. So for any one individual, right, I can get pretty close maybe with my predictions. I'm going to be off by whatever this individual error term is, right? Every individual would have their own kind of error term if I was just trying to predict their income based off of their years of education. Right? So what I'm going to try to do, and what I can think about visually, is once I have these estimates and I have this line of best fit, well, remember, all the points on this line, those represent predicted Y values. If I look at any one observation, here is the actual Y value, and here would be the predicted Y value on the line. So the only difference between those two things is this error term. Right? So when I draw this line, what I want to try to do is get a line such that all these errors, right, I can think about for every observation, there's an error term. I want to draw a line that minimizes those errors. Right? Because if I draw a line like way out here, right, you think about that's not my line of best fit because for every observation, right, I've got these huge error terms. So I want this line that minimizes those errors. So we're going to think about this as not just do I want to minimize those errors, right? Excuse me, I think I already drew this on the line. Yeah, we can think about, right, for any one observation, my actual Y value and this red dot, this predicted Y value, I'm going to have here like a positive error term, right? My prediction was off because the error term was positive, so the actual Y value is higher. If I think about an observation down here, my error term must have been negative because the actual Y value was below the predicted one. So when I'm trying to minimize these errors, I couldn't just simply add them all up because all the positive errors would cancel out all the negative errors, but they're still errors, right? It doesn't matter which way I'm off, I'm still off. So very similar to the variance, right? What we can do is actually minimize the squared errors, right? So if I think about for every observation, I'll take the actual Y and look at the difference between that and the predicted Y value, right? So that was kind of what represented my error term. I'll then square that, right? Square that error. So every single error now is positive, right? Even if I was off and the error was negative, now it's positive. But also very similar to the variance, what this does is it over penalizes really bad errors, right? So if I draw a line and, I'm off by 1, well, 1 squared is still 1. But if I have this line and the observation is, 10 away, well, it over penalizes it because 10 squared is 100, right? So by kind of squaring those error terms, I over penalize, you can think about it as like really bad errors from this line of best fit, okay? So kind of this is where, you don't have to, I'm not going to make you do this. We'll end up showing how Excel will do all this behind the scenes for us. But if we want to minimize this equation, right, let's plug in what the predicted Y value is. Well, that's just A plus B times whatever our X value is, right? Kind of missing that error term. I now have Y and X will be things I actually observe in the data, okay? A and B, I want to choose those values so that I'm minimizing this equation which is the sum of squared error terms. So I can basically do a little bit of calculus. If I take a derivative of this function in respect to A and B, right, I would kind of think about it, have like 2 equations, 2 unknowns, right? Set them equal to 0, I could solve that, okay? So if I kind of take derivative of this in respect to A and B, I could do a little bit of math and figure out kind of what the equation would be that would give me the predicted value for A and B that would minimize those sum of the squared errors or give me this line of best fit, okay? So we've already kind of thought about this, so I'll kind of skip. I did this up on the board, just kind of a reminder. So, we could think about one thing I didn't have in the other slide. Remember, Y minus Y hat, that's just our error term, right? So we'll take a derivative in respect to A and B, set them equal to 0, solve for it. Don't worry about writing these down. I'm just showing them to you right now. we could get the equations for how we find that predicted B value and how we find that predicted A value. Okay? Now, we could rearrange this. Sometimes if you're doing this by hand, it might be a little bit easier to do it this way. The thing is, we're not going to do this by hand. Maybe after the break, I'll show you how we could do this in Excel because it's not very hard. Right? Once I have this equation, I just look at my data and I say, well, take every single X value, subtract the mean, multiply that by every single Y value minus the mean, then multiply those two things together, add them all up. Like I can think about this as separate columns in Excel. Now, we don't have to worry about that because Excel is going to do all that for us. So I have these slides up here, but we're not going to ever do this by hand. I'm not going to make you do it by hand. I feel really bad that people used to have to do this by hand before they had computers. So I'm going to show you how we do this in Excel and kind of talk about a little bit of Excel stuff now, okay? So if I go to Excel, I put this GPA data up on Canvas. So we could think about, maybe I'm a college admissions board and I want to think about, I'm trying to predict what someone's freshman year GPA is, right? So this data set, these kind of has all these freshmen. And then we look at kind of what was their SAT score coming in, right? So I go to data, right? And you can see here I have a data analysis tab. Now you might not have that there. Excuse me, and these steps are kind of in Excel, but the way you add that is you go to File, you go down here to Options. Right? If you're on a Mac, I think the newer ones, I think it's under Tools, and you'll see once you hit Tools, you should see a similar option for add-ins. Okay, but in general, kind of non-Mac, I think it's File and then Options. Okay, so we hit this add-ins. Go down here to manage our add-ins. And the one you want, I have both of them in there now, I'll just put one in, is this analysis tool pack. So make sure, if you don't have it already, it'll just look blank. Click the box, hit OK, and now when we go to that data tab, it should be data under data analysis. Like I said, I think on some of the newer Macs, it should be under tools. Some of the older ones, if you have quite a bit older of a Mac, you might have to download something called StatLE, I think is the name. And then it would work very similar to kind of everything I'll show you once we click this data analysis tab. I would try to start figuring out, try to get that added in. Make sure you can get that analysis tool pack. If you're having any troubles with it, send me an email. Like I said, I know different generations of the Macs, it's a little bit different how you get there. So if you're having problems finding that, let me know. Or do a quick Google search of analysis tool pack, Mac, and whatever kind of Mac you have, but make sure you can try to, you're going to get that in there. I will have like kind of one more assignment I'll put up after Thanksgiving. It'll actually be pretty easy in Excel. I'm actually putting it out there. So like if you missed one, there's one more that's pretty easy for you to do, but it involves using this data analysis tool. Okay. So once we have that in there, it's really easy. So we hit that data analysis, we go down to regression, we hit OK. Okay. My Y variable, I'm trying to predict college GPA. So I'm going to select that column, click this little arrow. Now my X variable, scroll back up here, I'm going to select this SAT score. Right? I'm going to use that SAT score variable to try to predict GPA. I selected the labels, right? Those kind of label headings, those column headings. So I'm going to click that button. Now, if I hit OK, I'm going to put this on a new worksheet. You can put it on the same one and like specify where you want it. I usually just put on a new worksheet just to make it easy. So I hit OK, and it spits out all this stuff ahead of me, right? So these all represent something, but we don't necessarily need to know how, to use any of this for right now. What we're really focused on today is going to be this column, right? So when I think about those values of A and B, what I'll kind of generally refer to them as coefficients, right? Once we get an estimate for what those are, we're going to call them coefficient estimates, right? So here's my estimate, my coefficient estimate for the intercept or that constant term, A, right? Here's my coefficient estimate for the relationship between the SAT and my Y variable GPA, or B, right, the slope. So once I have these coefficient estimates, we can start to think about, I can make predictions with them, right? For example, if I wanted, let's say I wanted the predicted Y value for someone that, what's a reasonable, got a 1300 on the SAT score, right? So if I was trying to predict Y, well, my intercept is this guy, right? Actually, before I do this, let's make sure you guys can see this a little bit easier. So if I wanted to predict it, I've got my intercept, so I think about it this way. I could think about this as, I'm trying to come up with a predicted Y value, right? So in the context of my example, I'm trying to predict GPA. The intercept coefficient I got, A, was like 0.66. I think the slope is like 0.0019 or something. And my X variable is that SAT score. So all I have to do to get the predicted GPA of somebody with a 1300 on the SAT score is plug in the 1300 into that equation. So once I have those coefficient estimates in Excel, I could do that pretty easily. Right? I guess I could enter that into a calculator. But here, take the intercept, add that slope, multiply by whatever X value I'm interested in. Okay? So about a 3.17 would be the predicted GPA of someone with a 1300 SAT score, and I could play around with this, right, and get different values. Excuse me. So that's how we can use those coefficient estimates to start to come up with predicted Y values for any X kind of value we're interested in. Okay? Any questions on that? Or keep moving. Like I said, if you might have some issues with the Mac getting that data analysis on there, but email me, reach out to me. We can kind of figure that out if we're having issues with that. All right, so here's kind of the general steps. So let's think about another example, and we'll talk a little bit more about how we can think about what these coefficients are actually telling us. So I had this data set that had income and the number of days someone smokes marijuana each month, kind of self-reported. So we'll take it with a little bit of skepticism. So we've got kind of, it was a younger, a survey of quite a bit younger individuals, and so some of them, right, have very low incomes. I mean, these are like high school and maybe college students, really not kind of working a typical 40-hour week. But nonetheless, it's like an interesting kind of example to think about, okay? So the equation I'm trying to estimate is I want to try to predict someone's income solely based off of the number of days they use marijuana every month. So this is, we'll talk about, I don't know if we'll get there today, but definitely after the break, how obviously there's way more things that kind of affect income than just this, but this is the one thing we're trying to understand the relationship between. Okay? So I used not Excel, but a different kind of statistical package, and I just kind of wanted to present it to you. But we're basically, here's our Y variable, here's our X variable. It's going to give us that coefficient estimate or that slope between the number of days using marijuana and income. And it'll also give us that coefficient estimate for that intercept, or here, it kind of labels it as that constant, right? Those two terms are interchangeable. So we look here, and we see negative 253 is my coefficient on the X variable I'm interested in. So the way that we always interpret these coefficients, just kind of the general, is a 1 unit increase in my X variable would cause the predicted Y value to go up or down by whatever this coefficient is. So in the context of this example, using marijuana 1 more day each month, right, would cause the predicted income to go down by about, I don't know, $250, okay? Now, like I said, we also have to remember, this is just evidence of a correlation, right? We're missing a lot of other factors here, but we can get an estimate for what that correlation is, okay? The way we interpret the constant here is a little bit different, which is, if someone was, how do I get my Y value to just be equal to the constant? Well, if I plug a 0 in here, what's the predicted Y value? Well, 0 times anything is 0, so just the intercept. So the way we interpret the intercept is, if my X variable is equal to 0, this is kind of like where Y starts, right? This is the predicted value of Y if that X variable is equal to 0. So in this example, if someone uses marijuana 0 days each month, their predicted income would be $32,000. Okay? So that's how we kind of interpret these coefficients. I think I've kind of got that spelled out here. But, you know, the general rule is that constant or that intercept, the interpretation is if the x variable is equal to 0, that's the value of y, or predicted value of y. The slope coefficient is always if my x variable goes up by 1 unit, this is the expected amount that y is going to go up or down depending on if it's positive or negative. Okay. Now 1 unit is going to be very different, right? Here it was the number of days. If we had, you know, something in dollars, it's $1 more, or however the variable is measured, that would be a 1 unit increase. Okay, and that lines up with when I had the graph up earlier where I was like, if x goes up by 1, right, 0 to 1, the amount it changes is the slope. That's exactly what we're saying here. We're just kind of interpreting that, excuse me, a little bit, kind of saying it in English, as opposed to in mathematics more so. So the next thing we can do, these are estimates, right? We estimated these based off of data. So if we have like a sample estimate of something, like a sample mean, we can do some hypothesis testing with it. Now, we're not going to have to go through the steps because, sorry, I really could use a drink of water right now. It basically, anytime we run these regressions, we're going to get this output for the p-value. I'll show you on the Excel one we did, right? It gives us p-values. Well, notice this is like 2e to the negative. This is saying move the decimal point, use 2 and move the decimal point 166 spots to the left. So this p-value is basically 0, right? I mean 0.00 165 times and then a 2. These p-values are 0, so if the p-value is 0, I'm not really sure what test we have yet, but that's definitely going to be less than any alpha we can think of. We're going to reject the null. So what's the null hypothesis in these examples, right? Well, it's a little bit different than what we were doing before, but it's actually pretty easy because it's always the same, okay? So we could test for, is that slope coefficient greater than some assumed true value? Is it less than some assumed true value? Is it not equal to some assumed true value? But what we're always going to do, and I say most of the time, every time in this class, but most of the time in general, we're actually going to assume that that true value of b, the slope, is that's always equal to 0, right? So I'll write this out a little bit more formally so we can think about what our null alternative will always be, our null alternative hypothesis. So we'll always start out and assume that the value of this coefficient, right, the true, like we observe the coefficient estimate, but we're assuming the true value of that slope, right, the relationship between x and y, we'll always assume that it doesn't exist, that it's equal to 0, that there is no relationship between x and y. Then if we can get a coefficient estimate that goes against the null or shows that that slope is something other than 0, if we can find it's far enough away from 0 or far enough standard deviations away from 0, then we are able to kind of reject that null hypothesis. So if we're rejecting the null here, what we're really saying is we're rejecting that there's no relationship. Or if you want to think about it a little bit differently, we're saying we found significant evidence to support that there is a relationship, something other than 0, right? You know, if x goes up, y is going to change by something. Now, I'll leave it at that. So we're always going to have kind of this two-tailed test, right? And we're trying to find it if we can see if we can find a coefficient estimate that's different enough from 0 to be able to reject this assumption that there's no relationship between x and y. Okay. So if we look at this output, right? I've got kind of another one here. So we've got the birth weight of a child and whether or not the mother smokes while pregnant. Right? Well, here it's a little bit weird because our x variable now has changed a little bit, right? So we've got this variable of whether or not the mother smoked while pregnant is either a 1 or a 0, okay? 0 if she didn't, 1 if she did. So the way that we interpret this coefficient now, this slope, is a 1 unit change in our x variable, but now the only unit is going from 0 to 1, or going from not smoking while pregnant to smoking while pregnant. So if a mother that we observe, instead of not smoking while pregnant, smokes while pregnant, the predicted weight of the child goes down by 213 grams. If the mother doesn't smoke while pregnant, or this is a 0, then the constant, or the intercept, well, that's the predicted value of the birth weight of the child if the mother doesn't smoke, right? If this was equal to 0. So what if instead we want to know what's the test statistic? So if I look at the kind of previous data, excuse me, right, we've got a test statistic that's also given to us here, right? So how would we be able to find that? You know, if we're doing a hypothesis test, Excel and everything is spitting a p-value out at us, but how did it get that? Well, the thing about here is it also gives us this column. So here's our estimate for the statistic we're interested in, that slope. There's going to be some kind of variation in kind of the error terms that we were thinking about, and the standard error is a measure of that variation. So you can almost think about it as before, let's just do a sample, an easy one. So let's say we did right? This test statistic of a sample mean. We took the statistic we're interested in, subtracted the assumed true value of that statistic, the population value, and then divided by what this denominator was some kind of standard deviation for those sample means. So for linear regression, when we have this kind of coefficient estimate for the slope, well, we're going to subtract the assumed true value of that slope, but I said we're always going to assume it's equal to 0. So this almost just like kind of goes away, but technically it's still up there. And then we need to divide by some standard deviation of that estimate that we have. Well, what we're going to call that is that's our kind of standard error, right? Or that other column in Excel. So all I have to do to get my test statistic is take that coefficient and divide it by my standard error, which if I look at that output, if I have, well, we'll go back to the old one and then we'll talk about how we would find the new one. So let's go back to that income marijuana one. Notice that coefficient of negative 253. If I divide that by that standard error, so 250 divided by about 50 would be around 5, or negative 5, sorry. Sure enough, if the exact, if I don't round it, negative 5.23. So all I'm doing to get that test statistic is taking the coefficient, dividing it by the standard error. If I took the coefficient of the intercept, divided it by the standard error, it's going to be kind of close to 100, right? The exact value being about 96.7. Okay. So I'll go down to this other example, the birth weight one. I've got about what? Negative 213 as my estimate for the coefficient on the slope, 49-ish for my standard error. So divide 213 by 49, I'm going to get approximately that negative 4.36, right? So it's pretty easy to find these test statistics. In fact, if I give you this, if I give you some output like this and the question on the test is what's the test statistic here, should be an easy one. You just look at the variable, take the coefficient, divide it by the standard error. Now, finding the p-value would be a little bit harder. We have things like finding the degrees of freedom and looking it up on the student t distribution. But generally, I'm not gonna ask you to find the p-value on these. I want you to understand how to find the test statistic just so we can think about what would this, how does this kind of line up with the other hypothesis stuff that we were doing? But, oh, what do I want to do here? I think I want to go back to Excel for a second. I think I have some repeated stuff here. So we were, got 20 minutes left. Okay. So we already kind of walked through all this. This was just kind of talking about what we were trying to do, minimize some of the squared error terms. And then we kind of ended with, we could do some of this in Excel by hand if we wanted to, but like it's not fun, right? Even with just one variable, this is kind of a mess, right? So if that is a mess, right, we can think about if we actually wanted to, we can include not just one variable on the right-hand side there, but several variables, right? And why might we want to do this? Well, look, I mean, we know that SATs are probably a pretty good predictor of GPA, but there's a lot of other things that might even be better predictors, right? So just to ignore them doesn't make a lot of sense, right? And actually, we can kind of think about this example where let's assume that what we want to do is our Y variable, we want to estimate crime rates, and we'll look at kind of police force expenditures, right? So we might think that if we spend more on our police force, maybe we can keep crime rates down, crime rates down, right? The problem is, if you actually had some data on this and you estimated this equation, you're going to end up with that slope coefficient is actually positive. So what that would be saying is if I spend, I guess, $1 more on my police force, it's actually going to cause crime rates to go up. So why would this be the case? Well, that's because I'm thinking about it, even the way I just described it, as causal, right? It's not causal. Like, we can interpret these things and they'll sound causal, but we have to remember they're just evidence of correlations, right? It's that every $1 more I spend on my police force is correlated with an increase in crime. Now, for every unit that is higher of police expenditure, it's correlated with a certain amount increase in crime, but it doesn't necessarily mean it's causing it. So you think about in this example, what areas are more likely to be spending more money on their police force? Areas that already have higher crime, right? So this isn't necessarily telling us anything about the causal relationship. However, if we can start to control for other things that maybe pick up reasons why crime would already be higher in an area, like socioeconomic measures. So maybe we add in a second variable, which is something like the unemployment rate or average income in the area. Well, now what we can do is when we're thinking about the relationship between police force expenditures and crime, every other variable that we add in here on the right-hand side, it holds those factors constant. So now the interpretation would be something like, if police force expenditures go up by $1, holding constant the unemployment rate. So it's like looking at two counties, they both have the same unemployment rate. One of them spends a little bit more on their police force. What would the increase in that county's crime rates be? Or what would the change, in their crime rates be? And once I start holding some of these other characteristics or factors constant, well, now what I'll actually find is now that estimate on B actually becomes maybe what we would have thought it is, right? And negative, kind of closer to the causal relationship, right? Now, what we kind of called this before when we weren't including important variables is called the omitted variable bias. And we'll talk about that a little bit more in a second. But the idea is if we can add in more variables that matter, those estimates kind of will change because they're getting closer to a causal interpretation and not just a correlation. Right? So we kind of already talked through this example up on the board, but if we add an unemployment here, that helps out quite a bit. Right? Now the problem is, if I have several variables, I now need to get an estimate for each one of these coefficients. And I wrote them here as kind of beta, right? So beta 0 is my constant or my intercept. Beta 1 is the coefficient on my first x variable. I could think about this, beta 0 is A, and all these betas, I could write them as kind of B1, B2. It's just a notation thing, right? You typically, if you looked at anytime a linear regression is used, typically you see the coefficient estimates written as beta, okay? So the problem is we have to choose, we have to figure out, now it's like, I can't even give you a good visualization, right? It's not a line of best fit. It's like this, I guess if I had two, you could think about it, it's like a three-dimensional, and I'm trying to figure out the line that best fits the data there. But once I include, 4 or 5 variables here on the right-hand side, I've now got something I can't visualize. I've got a 5 or 6D kind of thing going on where I'm drawing this line of best fit. But you can still think about it as you are drawing this you're drawing this line of best fit through something you just can't really visualize, right? So how would we do that? Well, we're still trying to minimize that sum of the squared errors, right? Our predicted y value now is kind of a longer equation, and so we're going to have to take a derivative in respect to each one of these coefficients set them all equal to 0. Now I have n equations, kind of n unknowns. I can still solve that. It's just much harder, right? And so, you know, doing this by hand is a nightmare. Luckily, right, you know, I put the solution up there. You can kind of see, yeah, if you've taken some higher level math courses, this might make some sense. If not, it's going to just look like, you know, a different language. But it doesn't matter, right? Because we have tools like Excel and other statistical programs that can do this for us, do all that math behind the scenes for us very quickly, might I add. And then the interpretation is the same for those coefficients. It's just now, it's for every 1 unit x goes up, that beta, excuse me, that slope coefficient is the expected change in y from that 1 unit change in x. But now we get to add on holding everything else that we put in that right-hand side constant. Okay, I think I'll actually wait on this because I want to show you I want to walk through an example in Excel because I think this really kind of hammers home this idea of why adding in additional kind of variables is helpful, right? So let's say I have this story in my head that being a student athlete in college is, you know, I could think about maybe these individuals don't have as much time. They're not as focused on their classes. And so it's actually a negative, it's going to have a negative impact on their GPA, right? So if I'm thinking about the equation I want to look at is GPA is equal to A plus B times whether or not they're an athlete, right? And I'm thinking this slope could be negative. Now, it also could be positive, right? Maybe because I'm in a sport, I have to have better time management, or I've learned some time management skills, or there's literally higher incentives to me not failing my classes, right? So I'm not really sure what that is. And I say, okay, I'm going to try to figure out what that correlation is by running this regression where my y variable, I already had it selected, so it kind of kept it in there. So that's nice, is my GPA. And I'm going to look at that x variable of whether or not the person is a student athlete. So select that. I've got my labels, hit OK. Right? So we'll kind of call this athlete. So it looks like, right, that the effect of a 1 unit increase, now athlete here was just, if we look at the original data, a 0 if the person was an athlete, a 1 if they were, sorry, 0 if they weren't an athlete, 1 if they were. So when I look at the output, a 1 unit change would be going from not being a student athlete to being a student athlete. So it looks like if I am a student athlete, let me become a student athlete, my predicted GPA goes down by 0.28, which might not sound like much, but for GPA, right, it only goes from 0 to 4. Well, hopefully it doesn't go all the way down to 0, right? So I mean, this is a pretty big decrease. Okay? The problem is there's a lot of other things we didn't control for. Just in this small data set, like I don't have a ton of variables, but I've got things like high school rank, whether or not the person's an athlete, you know, their gender, kind of racial demographic identifiers, total credit hours, their high school size, where they ranked in their high school. So I've got all this other information, right? So let's say all I do even here is just include this SAT score variable. So maybe I think that, you know, student athletes, maybe there's differences among student athletes and non-student athletes in terms of just what their SAT scores are. So if I could hold constant what the SAT score is, that's like saying I have 2 students now and they both have the same exact SAT score, which is like my best measure of kind of like where their like intellectual ability lies. Now one of them is becomes a student athlete. Now what's the change, right? Before I wasn't able to hold kind of constant their SAT score. So I'm going to be able to show you a problem that we have with this data analysis package. So let's say I've got college GPA selected as my y variable, but now I try to just select, so I select SAT, hold the control button, I select athlete, and I try to select kind of both of these. Actually, that didn't do what I wanted, so I'll show you this way. So I select the SAT score variable, I go up, I also select that athlete variable, right? So I've got my 2 variables that I want in there selected. Now the problem is if I hit OK here, it's going to give me this contiguous reference. It's mad at me. Well, that's because, so get out of this, I'll hit cancel, go back up and show you what we need to do. When we're selecting these variables in Excel, they have to be right next to each other if we're going to include them on the right-hand side. So what I need to do, actually I'm going to insert another column over here. So I can move these around. So I don't want these variables in there right now. I just wanted this athlete variable. So I'm going to move my columns over so that now I can select the two variables I want are right next to each other. So now when I go to, get out of here, data analysis, I've got my Y variable selected, which is GPA. Now I have to, I'm going to select these two columns, right? Hit OK. Now it runs, and that's because it needs them to be next to each other, right? That's all. I don't know the exact programming behind why it needs that. My guess is something about the way that the data is kind of stored in Excel as a matrix, and so if you want to use variables, they need to be right next to each other. So let's look here. Oops. Now what we can interpret this as is holding constant someone's SAT score. If they're now a student athlete, right, this is a 1 unit increase going from 0 to 1. If someone becomes student athlete, their predicted GPA now only looks like it falls by 0.05. So a much smaller drop, right? And that's because we were able to hold constant or like look at two individuals with the same SAT score, right? Now what's the effect of being a student athlete? And the interesting thing is, if we look at the original, not only was this a much larger coefficient, much larger kind of drop, negative value, the p-value is pretty much 0, right? E to the negative 9 move this decimal point 9 places to the left. So this was a p-value of 0. We could easily reject the null at any level. And remember, the null is that there's no relationship. So we're rejecting that. We're saying, no, there is a relationship. Like we found strong evidence that there is a relationship. But notice, once we included that SAT score variable as a control, it dropped the slope coefficient, but also our p-value is 0.25. At conventional levels, 95, 90, 95, and 99%, right? My alphas would be 0.1, 0.05, and 0.01. I actually failed to reject the null. So if I fail to reject the null, what I'm really failing to reject, remember, is that the relationship is 0. So with high levels of confidence here, I can't actually say that there's any relationship between whether or not someone's a student athlete and their GPA. Right? And if I want to keep running with this example even further, and I'll rename this one SAT only, because if I have this original kind of data in here, what I could do is go to that regression tool. And now for my X variables, select all controls that I have in my data set. Right? So I'm going to select all of them, hit OK. Now it spits all this out at me. Now, the interpretation on that athlete variable would be if I hold everything else in this equation constant. So it's almost like this thought experiment of I'm looking at somebody with the same SAT score, two people with the same score on this verbal math test. They're either both female or both male. Their race is the same. They have the same total credit hours. They went to the same high school high school with the same size. Don't worry about this. I squared the SAT score. It's just for something else we might talk about after break. They go to the same, had the same ranking in high school. So all those other things are identical, but one of them is a student athlete. What's the predicted change in their GPA? So now we've got like a much more apples to apples comparison in terms of this thought experiment. And now we see that the estimate is actually positive, right? And not only is it positive, it's very significant, right? That p-value is less than 0.01. So with 99% confidence, I could tell you that the relationship isn't 0. In fact, it's positive, right? So we went from, if we're just using linear regression, a very naive approach, well, yeah, that correlation might look very different than when we include a bunch of additional variables, because it's not only picking up the relationship between being an athlete and GPA, but all the other things that might be correlated both with being an athlete and with your GPA, right? So once we control for all those other factors, right? So I'll kind of call this all. I'll put this up on campus after today's class. Once I control for all those other factors, and now I actually have that being a student athlete might have a positive effect. Like I mentioned before, maybe some time management things, you know, once I'm looking at kind of individuals who are the same on all these other dimensions. Right? So, this kind of just shows, we have the data, it's very useful to kind of control for things that we think are going to be correlated with or be able to predict that Y value, okay? I think that might be where we stop today. Well, I'll show you kind of this. It's this idea of correlation versus causation, right? If I'm missing some things, right? We just saw that if I started to include additional control variables, that coefficient on athlete completely changed, right? But maybe there's still some other important variables that I've left out, and maybe it would actually go back to being negative, right? So this idea that just because we see two things are correlated doesn't mean that it's causal, because we might be leaving out other important factors, right? So I always like this little graph where you can look at autism rates and organic food sales. I mean, this is like a perfect correlation. I don't think anyone's going to argue that autism is being driven by organic food sales. Right? There might be someone out there who knows. There's a lot of crazy people out there, but that's not a causal relationship. It's likely that these are correlated because maybe there's other things that are driving both of these factors, right? Like we have higher incomes, we're spending more on healthcare, and so maybe we're better identifying cases of autism, but we're also more concerned with our health, so we're looking for other sources, to improve our food quality or something like that. So we'll talk a little bit more about this kind of idea of correlation, causation after the break. We'll kind of revisit. I'll probably give you a couple more examples. We'll look at, doing a couple more things in Excel with linear regression that first week after break. Then that second week, I'll review. So after Thanksgiving break, I'll get some practice exams up there. And then kind of the way that the final, we'll talk more about, I'll post a video talking more specifically just about the final. But you're going to have kind of a block of time over that third kind of final exam week. So it won't be like just on one day. It'll be kind of like what we've done with the other two exams, where there's a 48, 72-hour kind of time period where you're able to kind of take it whatever best works for your schedule. So that's kind of where we're going. Thanks for those of you who showed up. This will be the last in-person class this semester. Be safe over break. Feel free to reach out over any time. I'll be available all the way until the semester ends. And I'll see some of you on Zoom Monday after Thanksgiving. All right. Enjoy your holidays.